Hi, welcome back to Hijax, Act 1. This is Lecture 5, High Stateful Optimization. So this is the fifth and final lecture of Act 1, where we've been touring through some of the kind of basic elements of the JAX programming paradigm, from pie trees to procedural random number generation to vectorization, and now we'll be looking at a common pattern for managing state for stateful optimizers in deep learning. You'll be pleased to hear that we're not going to be typing out a full neural network architecture from scratch line by line this time, like last time. In fact, we're going to be bringing the SimpLeNet code base from the last lecture as our starting point for this lecture. And we're going to be adding a new feature on top of it. That new feature is the Atom Optimizer. The Atom Optimizer is an adaptive stateful optimizer that is an enhancement of stochastic gradient descent that was proposed in a paper by Diederik Kingma and Jimmy Barr about 10 years ago. And it's still used in practice today. It's still one of the sort of most generally well-performing optimizers that is used in deep learning practice. And so we're going to be implementing this optimizer basically using the equations in the paper, which is why I've got the paper up. And yeah, the one problem with this optimizer is that it's stateful. And as we know, JAX doesn't allow mutability. So we need some way to keep track of the sort of state of this optimizer and how it changes as we're training. And, you know, we've been handling some stateful objects like neural network parameters and random number generation. This will be another chance for us to practice this pattern in JAX, and that's really the goal for today. This is also a good chance to become even more familiar with pie trees and tree mapping because this optimizer, we're going to write the functions of this optimizer in a way that they're going to work with any model that is implemented as a pie tree, no matter what the pie tree structure is. And that's just like the functions in the JAX API, how they work for arbitrary pie tree arguments rather than just assuming a specific shape or structure. And we're going to write a flexible optimizer in the same way. So let's get right into that. I'm here in the Hijax GitHub repository, or Git repository, which you can get from GitHub to follow along. I'm in the Hijax virtual environment, which has all of our libraries that we need installed already. And we're in the Hijax repository itself. We're going to go into lecture 5, and you'll see there's actually nothing here because the first step is I'm going to copy across the what I've now put in the solutions from lecture 4, the SimpLeNet, and I'm going to call it, but you might have this in your lecture 4 repository, folder. I'm going to call it SimpLeNet atom.py, and this is going to be the starting point for today's lecture. So this is what we developed last time, and you'll be familiar with it from the last lecture, but just to flick through, we've got a main loop where we load some training data, we initialize a big model, and we do a bunch of training. And the big model is a SimpLeNet. It has all of these different components that we defined painstakingly line by line, including putting them all together here. We have cross-entropy and batch accuracy, our metrics that we defined last time. And we have some visualization code that creates these nice dynamic visualizations of the probabilities of different classes and also some learning curves for the accuracy and the training loss. And so going back up to the top to look at the training loop, this is where we're going to put where we're going to put Atom in. So what we want to do is, instead of using stochastic gradient descent, where we basically compute gradients every step, and then we use just those gradients to determine the update that we make to our model, we're going to want to apply compute the gradients and then pass them to an adaptive optimizer that is going to kind of internally track some momentum style terms, and then we're going to apply those. That's going to tell us what update we should make to the model. We're going to give it this gradients, it's going to update an internal state, and then it's going to tell us what update we want to make to our model. And then we'll keep that updated state, and the next step, we're going to give it the new gradients. It's going to look at those and the old gradients and decide what to give us. So that is the general pattern that we're going to set out here. And so to get this to work, we're going to need a few things. First of all, we're going to need some code here initially before the training loop to initialize the optimizer. And we're going to write a function that basically does that basically represents the initial state of an optimizer, and then we're going to call that code here to set up the optimizer beforehand. And then we're going to have a variable coming out of this that's going to be called something like opt_state, and so we'll fill that in later. And then when we come into this code, after we compute the batch loss and grads, instead of just directly applying the grads, we're going to update optimizer, get model update, and apply to model. And so we'll have something here like opt_state and update equals something where we give the new gradients to the model, and it's going to give us back the update that we want to make to our model. So like instead of grads, we're then going to use this update. And this update, we're going to set it up so that instead of applying it with the stochastic gradient descent rule, we're just going to directly tree map over the model and just directly add the update u. We're going to just directly add that to the weights. So we'll have weight plus u. And in fact, I could simplify this. I could just write model equals jax.tree, or maybe I'll just put it here. This lambda u, wu equals w plus u. This is just jnp.add. And so this becomes my update, which is very simple. The thing is, I need to get that update from the model, from the optimizer, sorry. And then this opt state is going to be carried through to the next training loop. We're overriding the initial opt state, and we're creating a new one here. And then that's going to go through the next loop where we'll again override it, and this will keep being updated throughout the loop. And so our job now is to basically fill in what goes here in the ... dots. And so I'm going to leave these sort of holes in our code now. I guess I can call them to do instead. And we're going to fill those in. And so let's go ahead and see what we have to do to implement Atom like this. And so let me just flick through to my cheat sheet. Keep us on track. So let's go to before the architecture but after the training loop, so we're staying nice and close in the code, and create a new section that is Optimizer. And so we're going to define a class that we're going to we'll just call it Atom. We don't actually have to make this a pie tree because we're not going to do any tree mapping over it or pass it to any gradient functions or anything like that. But it might be nice to just have it as a pie tree anyway, and we certainly want it to be a data class because that is a nice way to sort of, I like the syntax for data classes. So we're going to make it a data class, and then we might as well register it as a pie tree as well because it could be. So jax.tree, treeutil.register data class, and this will register it as a pie tree. Now, Atom is a stateful optimizer, and we can flick over to the paper and see what the state involves. And so we don't need to read, but you can if you want. It's like a well-written and interesting paper. The things that we need are a step size, some other hyperparameters, exponential decay rates for moment estimates. These are going to be like the hyperparameters of the optimizer, and they're not going to change during training, but we do need to remember what they are so that we can do the things. But they're like stateless in that once we set them at initialization, they stay the same, so that's fine. But what we're going to need is internally, we're going to need a first moment vector that has a parameter for each. It has an individual floating point number for every parameter in the model that we're training. And also a second moment vector that does the same. We're estimating the second moment of the change of the parameter. And we're going to need to keep track of a time step. And then this is the code for the actual training loop, and it's showing sort of how we're going to go about updating this first moment estimate and this second moment estimate as time increases. And we're going to need to implement these update rules in JAX. And then that also, this pseudocode, by the way, also shows us what we need to do to derive the update that we're going to give. We're basically going to be returning this thing, and this is what we're going to be adding to the each of our parameters to get the new parameter. So this pseudocode is sort of telling us all we need to know, but we're going to walk through it step by step in code. So the components of our class here are going to be an array called moment1, which we're going to use a new type for this. So I haven't imported it because we didn't need it last time, but jax typing has this pi-tree type, which you can sort of use to represent arbitrary pi trees. So where we've been using, like, we could use SimpLeNet for this actually, but let's make this generic so that it works for any model. So if we go back to moment1 and say this is going to be a pi tree, and I'm going to say that this pi tree has a particular structure that I'm going to call model. And then I'll use this sort of string. This is just annotation. Again, this isn't really, we're not validating these types at all, so this is just for our own benefit. But we're going to define moment2 as well, which is going to be a pi tree, and I'm going to say it has the same structure. It also has this model structure, whatever that is. It's like an abstract thing at the moment. Okay, these are the sort of parts of our state that we're going to be updating. I guess there's one more part of the state that we're going to be updating. We're going to have this optimizer track how many steps there have been in optimization, which it uses for some normalization. Then we have the actual hyperparameters. So these hyperparameters, alpha is a float, it's our learning rate. Beta 1 is another float, it's one of these exponential decay rates, and beta 2 is yet again another float. So these are not going to change during training, but we're going to be using like self.alpha, self.beta1, self.beta2 in calculating the updates of the internal state and the updates for the model that we give from this optimizer. Now, we're going to need two functions, one to go in each of those holes up in the training loop. And so one of those is going to be an initialization. And we might as well use the same sort of pattern we've been using for our neural network parameters of defining a static method called init that is going to take a model as input this time. And that's going to tell us the structure of the pi tree we want. And then it's also going to take some values for these. Oops, I need a square bracket there. It's also going to take some values for these hyperparameters. So that alpha is going to be a float, beta 1 is going to be a float, and beta 2 is going to be another float. And then it's going to return a self. And so that we'll make sure that that is an initialized atom object. And so let's do this. So we can go ahead and write this out in one go because it's not going to be super complex. And you'll notice there's no key coming in here. There's no random initialization going on for this optimizer. Instead, we want to define the moment1 as, this is interesting. What we basically want is a copy of the parameters of this model. Remember that this moment1 is going to be a first moment vector, and it's going to have the same size as the initial parameter vector. Our vector is actually a pi tree of vectors, so we need to make sure this has the same structure as the model. Now, one way to do this is to, initially it's going to be 0 for all of the parameters. So at least there's not going to be any complex random initialization or anything like that. So how can we take an arbitrary pi tree, which is a structured kind of container, nested container of jax arrays? How can we turn that into a pi tree that has the same structure, but all of the arrays have been replaced with 0? And one way to do that is to do jax.tree.map and map the jnp.zeroslike function over. So zeroslike, if I take zeroslike and I give it an array, it's going to give me a version of the array that has the same shape and data type, but all replaced with zeros for the values. And so it's exactly what we want for each of the leaves. And I don't even need a lambda because it just already has the right shape for this. So I want to map that over the model. And that is going to give me a pi tree that has the same structure as model, but where all of the leaves have been replaced with the output of zeroslike, which is going to have the same shape and data type as the elements of the model. And I'm going to do the same thing for moment2, which also also initializes to 0 in the atom pseudocode. Okay, So that's the complex initialization. Everything else is kind of simple. So we have this time parameter that's just going to start with 0 steps. Obviously, we have alpha, which we got from the input, and the same for beta 1 is beta 1, and beta 2 is beta 2. So this is initialization done, and we can go ahead now and go back to our before our training loop, where we want this opt state, which is really this value of this atom, is this class, this data class atom is going to be our opt state. So we can say atom.init and then pass in the things that we needed. So the model equals, well, we've got it called model, and the alpha, we're going to need to decide what alpha to use and what beta 1 and beta 2 to use. We better just give that as a hyperparameter that we can set via the command line. So I'm going to add some parameters here. I'm going to add, well, I've already got learning rate. I might as well use the same name. But then I've got, I want to have like atom beta 1, which is a float. And a good default for this, they actually say in the paper, and this matches the recommendations that I still see around today, 0.9 is a good default. And 0.999 for beta 2 while we're at it. So atom beta 2 float equals 0.999. But if I did want to change these parameters like the learning rate, I've added them to my main, so I can do that with the command line now. And so let's flick back to where we were initializing this and say I'm going to say the learning rate and then atom beta 1 and atom beta 2. So if I wanted to specify different values on the command line, that would now come through to the initial optimizer state. Okay, so this opt state is just an atom object. That's what we've kind of decided now. And so the next step is to go into the code and see we need a function that is going to sort of probably be a method of the opt state. And then it's going to need to take in something about the grads. We'll call this update, I think. It's going to need to take maybe the new grads, and it's going to need to output, it's going to need to update the internals and return a new modified version of the training state so that next time we call that version, overriding this one. And it's also going to need to give us the model update back. Actually, I might make it do this in the other order to match my code. So just to make sure I don't screw anything up later. So we'll say it's going to return a model update and then the new opt state. And then you could think of this as kind of like the convention that we've been following for the jax random split. And by the way, some people use the other convention because this is sort of symmetrical. But in my case, in my code, I like to have the key batch because this is sort of readable. It makes it part of the line. This is the new key that I'm getting. And then we kind of, it's like we're updating this old key. And that's coming out second. So I'll just keep that convention here, where I give the model update and the new opt state overriding the old opt state. And I guess just keep in mind that this update here is corresponding to updating the optimizer, and this update is corresponding to the one we're going to use to update the model. But I guess that's clear. Okay, so now let's actually go ahead and implement this update method with this shape in mind. So let's flick back down to our atom class, and we'll add a new function update, a new method, and it's going to have an input type, I guess, self, and also grads, which is going to be, by the way, a pie tree of the same shape as model, because remember, that's what our gradient descent is going to give us. Our autograd is going to give us for gradient descent. We're used to that already. And then that's the only inputs that we had, and the output is going to be a tuple of, we made sure that we were giving a model update first, so that's going to be a pie tree of the same structure as the model, and then we need to give a self out afterwards. So a self, that's going to be what we use to overwrite the atom. So we're kind of going to create a modified version of this state with updated moment 1, moment 2, and time values, and then use that to sort of update. So this method is going to first compute this model update and then compute the new state. Well, actually, I guess I might do it in the other way around. First computing the new state and then computing the update, because that's what works a little bit better with the code, with the pseudocode, I mean. So let's do that. So let's update the optimizer state. We'll compute the new opt state. And then let's compute the model update from the new state. So let's go ahead and do that. So first thing to do is to say we're going to have a new time that's going to be the old time plus 1. Every time we call update, we're going to increment the time by 1. Easy. Next is not so easy. We need to update the moment one. And we need to update this in a way that's defined by the pseudocode. So I'm going to flick back over to the pseudocode and have a look. We've done this so far. We've got the gradient, which is the gradient of our stochastic objective at time step t. We've sort of done that externally, and so we've passed this into the update method. The update method's current job is to find the new value of m and the new value of v, the first and second moment estimates. And it tells us that what we should do is we should mix with the beta 1 parameter the old moment 1 with the new gradient. And then for moment 2, we should mix with the beta 2 parameter the old v t minus 1, the old second moment with the squares of the gradient. And so let's go ahead and implement that. But there's one problem, is that this grads and this moment 1 is self.moment1 is a pi tree. So we're going to need to use jax.tree.map again. So let's go ahead and do that. We should not be afraid of jax.tree.map. Remember, the syntax for jax.tree.map is we need to give a function, and then we need to give the trees that we're mapping over. So the function that we're mapping and we're applying to each leaf is just going to be looking like this. It's going to be sort of an interpolation with beta 1 as the interpolation parameter between two values. But these have to be the leaves of the input pi trees. So we're going to need to define our lambda, which is going to take m1 and g, which we'll use these short names for the leaves. And then it's just going to do self.beta1 times m1 plus 1 minus self.beta1 times g. That's easy enough. And then we need to map this over to sort of get these parameters coming in. Self.moment1, which is the current value of moment 1, because we're defining this new one here. And then we need to also map this over the grads, which has come in as an input. So this will take each pair of corresponding leaves, apply this function, which will do the mixing that we need, and then send that through to the new value of moment 1, which in a moment we're going to then apply to the optimizer state to create a new optimizer state. And so we'll do the same thing for the second moment estimator. So lambda m2g, we call it, self.beta2 times m2 plus 1 minus self.beta2 times g squared. So we'll just element-wise square there. It explains that this is an element-wise squaring operation in the pseudocode. All operations on vectors are element-wise. Okay, so this is going to map over self.moment2 and grads again. And then we've got our updated parameters. And so once we've done this, we can actually compute the new state and we would be ready to return it. And we'd be ready to return this part. And we just need then to compute the model update, which there's a few more equations for. But we can already go ahead and compute this new opt state, which is going to be, one way we could do this is we could say this is an atom, and it's going to have this new value for moment 1, and moment 1 equals moment 1, and moment 2 equals this new value moment 2, which we have as the local variable, and time equals t, which is our new value of time. And then we could go ahead and copy across the values of the other arguments. But that's a little bit annoying, especially in general. It might be annoying to sort of update data classes like this if you have a lot of arguments and you're only changing a small number of them. In this case, we're changing half of them, so it's not so bad. But there is a faster way to do this, and that is to use data classes .replace, which is going to then take a data class, so we can give this self, and it will take a dictionary of updates, sort of keyword arguments that we can use to update this thing, and it will perform a copy and then give us back a new version of the data class that has the changes that we wanted. So if we use data classes replace here, that will save us a few lines of code. So then that's all. This is the only things that need to change. This will then keep the values of alpha, beta 1, and beta 2 from before. And so that's done. So we can now think of this new state as the next optimizer state. And when we eventually get to it, we're going to return some update and also new state, making sure that that's the second thing to match our type that we planned. Okay, so the next step is to compute the estimators, the model update. And so let's have a look at the code and what that requires. So the pseudocode says that we should update the parameters by adding this value, which is a negative alpha times m, the moment one hat, and the square root of the moment two hat, plus an epsilon to make sure this division isn't a division by 0. And this hat is going to have a scaled version of the first moment estimate and the second moment estimate. And the way this works is we're going to divide by 1 minus the teeth power of beta 1 and the teeth power of beta 2. And the purpose of this is to correct a bias in the first and second moment estimates, which is present because we initialize them to 0. And so if we just over time, this bias will become less relevant, and we can decay the amount that we're sort of scaling by, making it closer to dividing by 1, which obviously does nothing. But we're going to take the values that we computed and then just scale them a little bit to make sure that they are going to be unbiased. And this was a method that was sort of developed in this paper to make sure we had unbiased estimates. And so let's make new values of our estimators, moment 1 unbiased and moment 2 unbiased. And this is going to be implementing this, this scaling operation. So we're going to take moment 1 and divide by 1 minus self.beta1 to the power of t. Except we can't do this because this, remember, is a pi tree. And so we can't do an operation like this. We need to tree map the operation. So jax.tree.map of a lambda that is going to do the same thing. It's going to take each leaf of moment 1 and divide it by that. And then we'll map this over moment 1. And so that applies it to all leaves. And we get a new version of the pi tree where this operation has been done to everything. And we might as well go ahead and copy this and make sure we do same thing for moment 2. So make sure I change all the 2's to 1's. So here we go, all the 1's to 2's, except for this one, which is really a 1. And this one does, though, need to be beta 2. And we need to map this over moment 2. So I could also, alternatively, by the way, I could be using new state.moment1 here. But this is just a little bit shorter and makes it less dependent on the order in which I define the new state versus compute the model update. And so I'm going to use moment 1 and moment 2, the local variables instead. Okay, so now we've got these unbiased estimates. This is the m hat and the v hat. We can go back to the code and see again that the update is this expression. So we now just need to compute this expression and return a pi tree of updates where each update has this form of negative alpha times the corresponding leaves where we compute this expression. So this is going to be one last tree map. And so we can call it model update is equal to jax.tree.map, where we go lambda m1, m2. We're going to map over both the moment 1 or the moment 1 unbiased and the moment 2 unbiased. Let me put that here. So moment 1 unbiased and moment 2 unbiased. And for each of those leaves, we're going to compute negative self.alpha times m1 divided by the square root, jnp.square root of the moment 2, and this is an element-wise operation, so that's fine, plus an epsilon, and this is just to make sure it's positive, and they recommend using 10 to the minus 8. You could make this a hyperparameter. I think it's probably fine to just hard code it here. And then this should be everything we need to implement Atom. Like, we should be basically done now. So let me just return the model update, and then we can go back up to the part of the code where we were toying with the optimizer. So we're updating the optimizer. Optstate.update is going to internally compute the new moment 1 and moment 2, and then a new opt state that has the new time update and is going to keep those changes to moment 1 and moment 2 and the time into the next iteration and return it here in opt state, overriding the previous opt state. It's also going to take those updated moment estimates, rescale them to get rid of some bias, and then return a model update for us. And we're going to then apply that model update using one more jax.tree.map to the model. And so this should be done, and we should be able to now run this. So let's see how that goes. We've got SimpLeNet Atom. Run it. There might be some typos. We'll figure it out. Parameters, initializing the optimizer, and training. It might be working. Here we go. I don't know if you remember, but it took us until the end to get to like 90% earlier. This cross entropy loss has dropped way faster than before. Previously, it was a pretty gradual decline. We're already way above the sort of losses that we were getting to at the end of training last time. So this optimizer seems to be doing something right. And we'll see where we end up. When I did it in testing, I was getting a slightly higher score, and I was actually correctly classifying this image. It looks like with the random seeds, maybe I've split my keys slightly differently than when I did this previously. And on this random seed, I haven't gotten quite as high, but it's okay. This is still higher than we got in the last tutorial. Remember, we topped out at about 90.9 or something like that % accuracy on the first 1,000 from the test set. But this is pretty good. This is better than last time. We've gone 4% up just by changing the optimizer and changing nothing else about the hyperparameters or the architecture. So I think that's enough for today. It was a long lecture last time, and we've kind of reaped the benefits this time by having a big code base that we could just come in and make this small change of implementing this optimizer. There was a lot of jax.tree mapping. We learned to use data classes replace to update sort of some small part of a data class without having to update the whole thing, and that saved us a few lines of code. And then we were able to integrate this, most importantly, into our training loop without any mutation going on anywhere. We're just copying and overriding. And when we eventually get to using JIT, that's going to be lightning fast too. So that's enough. I'll leave you with a challenge. So the challenge this time is to do a slightly more intricate stateful optimizer yourself. And so there are a couple of ways you could make this more intricate. One thing you could do is you could add a learning rate schedule, which is a more modern idea that's been used in deep learning, where you sort of gradually start from a very low learning rate, and then you maybe like gradually warm up to a high learning rate, and then you go back down to a low learning rate. And this can help convergence. I'm not sure how much it'll help in this problem, but it could be worth trying. And so in order to do that, you would need to kind of track what time it is when you decide what learning rate to use in the model update that you return from your optimizer. Another option, which is sort of the option that I had sort of planned, is to do atom with weight decay. And so weight decay is effectively an extra term in the loss. You can think of it as an extra term in the loss, or you can think of it as you don't have to compute this gradient because the gradient is sort of so simple. It just turns out that it means you should take a step uniformly towards the origin when you do your model update. And so you would have to figure out what that update should be. Maybe look up atom with weight decay, which is sometimes called atom W. In some, like for example, in PyTorch, that's what it's called. And then you could initialize an atom W optimizer that, when you have the update method, computes the update, including this weight decay term that sends the weights, sort of decays them a little bit towards 0. And you may then have to provide the current model weights to get the magnitudes that you need, and you might have to do some tree mapping to find the model updates. And so this would sort of slightly change the API that you need, but this would be a good example of seeing where you have to thread like this state through. And so if you want to do learning rate decay and or learning rate schedules and or weight decay, that would be a suitable challenge, I think. And that concludes Act 1, actually, and so I'll see you next time for the first lecture of Act 2. Bye!